In this lecture, you are going to study crystal direction. So you need to find direction of the crystal. Why to find direction of the crystal? Why to find direction? That is because many properties of the crystal are directional. Okay, many properties are directional of the crystal. And to correlate these properties with crystal structure, you need to find crystal direction. So there could be many directions just like planes, and so we have to find Miller indices of the direction. In the last lecture we studied how to find Miller indices of the plane. So here we will study how to find Miller indices of direction. So it is Miller indices of direction. What is it? Miller indices of direction to show, let me draw first the diagram for it. I am showing the axis, and in that I am going to show a directional vector. So these are the three axes x, y and z. Obviously this is the origin O. Then in this is the direction. Let us say this is the directional vector r. R is the directional vector. Then Miller indices of this direction, which I have shown in this diagram, is nothing but vector component of direction resolved along each of the three axes. That is the vector component of the direction resolved along each of the three axes, which are reduced to smallest integers and enclosed in square brackets without comma. And they are the Miller indices of the direction. It's very simple way to find Miller indices of direction. We have to just find vector component of direction resolved along each of the three axes. Then we have to reduce that vector component to smallest integers and then enclose these three integers in the square bracket without showing the comma. Now in this diagram, R is the directional vector here. R is directional vector which is passing through origin. So any direction is passing through origin. And then you can express this directional vector expressed in terms of fundamental translational vector. A bar, B bar and C bar. If A bar, B bar and C bar are the vectors. They are fundamental translational vector. It's not negative sign there. And these fundamental translational vectors form crystal axis. So let's write R. R is equals to UA bar plus VB bar plus WC bar. In this case, A bar, B bar and C bar, as I said, are fundamental translational vectors, and this U, V and W are integers. Then Miller indices of the direction R is nothing but you have to enclose these integers U, V, W in the square bracket with condition, and that condition is their common factor should not be more than unity. Then this UVW are called Miller indices of direction. This UVW are Miller indices of the direction. And suppose if you want to find direction, then to find the directional vector, what you have to do is you have to start the journey from the origin. Then you have to move distance UA bar, distance UA bar. This A bar is just indicating the crystal axis. Then from that point, you have to move distance VB bar along the y-axis, and from the y-axis, from that point, you have to move distance WC bar along the z-axis, of which U, V, W are the Miller indices, and this A bar, B bar and C bar just indicating the crystal axis. And so the direction is the line or vector passing through origin and that point, so obtained, is called the direction, is the way you can show the direction. This is the way you can show the direction. Now, as I said that their common factor should not be more than unity. It means if Miller indices are 4, 2, 4, then it is wrong because their common factor is more than unity. And our condition is common factor should not be more than unity. So you have to reduce this to 212. As you can see here, when you reduce that to 212, the common factor is not more than unity. Other examples say say 200. This is also wrong because common factor is more than 1. So we have to reduce this to 100. Let me show some examples. Let's draw this direction. Again you have to draw the direction in unit cell. So if you want to show this direction, you have to first draw the unit cell. Let me draw the unit cell. So this is the unit cell, and in this unit cell we are going to show direction whose Miller indices are 212, 212, and I will simultaneously write the steps how to draw the direction. So step one is, first we have to draw the unit cell. Draw unit cell. So that is already drawn. And step 2 is select origin. You already learned how to select origin in Miller plane. Now in this case, the Miller indices of direction all are positive. So obviously we're gonna select this as a origin. So origin is selected. Once origin is selected, then step 3 is mark the axis. Mark axis. So the axis are, as I told you, this should be always your x. Never change the direction of x axis. This should always be y, and this side should always be z. So these are the direct x, y, z axis, and that is our third step. Then in this case, very important step is step 4. In the step 4, you have to select value of a. How much should be a? That we have to select. Remember that in case of Miller planes, a is always 1. But in case of a directions, select a is equals to the maximum index. Select value of a, and that equals to maximum index value. Now in this case, Miller indices are 212, maximum number is 2, so you want to select a is equals to 2. So once the value of a is selected, then step 5 is, I will say, start your journey. Start journey. From origin. You have to always start from origin, and you have to move distance u. If x index is u, then you have to move distance u along the x-axis. From that point, move distance v. V is your y index of direction. So you have to move distance v along y-axis, and then from that point, move distance w. W is your z index along the z-axis. So let's move that in this diagram. So we are going to start our journey from the origin. So our value of a is 2. So edge length of this cube is 2. And we have to move that distance 2 along the x-axis. So we will start from the origin. Let's move distance u, that is 2, along the x-axis. Then we got over here at this point. You have to mark your path by the arrow symbol. So this way you must show the arrow. Then from this point we have to move a distance 1 along the z-axis. This total distance from here to here is 2, and so let's say up to here the distance is 1. So you have to move distance 1 along the y-axis. You got this point. And from this point you have to move distance 2. Z index is 2. And distance from this point to this point is 2. So you have to move distance 2 along the z-axis. So you reached at this point. Must show the arrow. Must trace your path by arrow. So you got this point. So that is the final point. Then Miller indices of direction is 212, and so the direction is you have to draw from the origin and through the point so obtained. So this is the direction 212, and as I mentioned all the steps, let me write step 6. Draw directional vector from origin and through the point so obtained. So we got this point, this point you got, and then we have to draw the direction from origin and through that point. So that is the direction 212. Let me take some examples, more examples. So first, let's say that you have to draw the direction bar 312, and this direction you have to show in the unit cell, and hence you need to first draw the unit cell. So let me draw the unit cell. This is the unit cell. Let me copy this. I will be needing this again and again, so I will copy this. Okay. Now unit cell is drawn. The next step is we have to decide the origin. Now we have to decide the origin in this way. We need minus x plus y and plus z. So if you select this as the origin, as you can see, you get the minus x. Why do you say it is minus x? Because if this is the origin, this side of x is positive and this side of x is negative. So if you select this as the origin, you get negative x. Similarly here, you get positive y because this side of y is positive, and you get positive z. This is z. This side of z is positive. So first step, draw the unit cell. Second step, select the origin. And third step is mark the axis. And the fourth step is we have to decide the value of A. And this A should be equals to maximum index. As you can see here, maximum index is 3. So A is equals to 3. Then let's start the journey. We have to travel a distance minus 3 along the x-axis. Our A is 3, so this complete distance we have to travel. Show the arrow is null, and you reach at this point. From this point, you have to travel a distance 1. Your y index is 1. The distance from this point to this point, we have taken 3. And so 1/3 distance we have to travel, and 1/3 may be over at this point. So travel distance 1 along the y-axis. And from this point, you have to travel distance 2 along the z-axis. From here to here, the distance is 3. And you have to travel 2. So that 2 would be around over here. So you reach at this point, show the arrow. Never forget to mark it by arrow. So this is the point, final point. This is the final point you got. So you have to draw the direction vector by which is passing through origin and through the points so obtained. So this is the direction bar 312. It's very simple to draw the direction. I will take one more example. Let's say the index is, I am taking randomly, Miller indices of direction is say plus x-axis, let's say 2, bar 2 and bar 1. 2 bar 2 bar 1, and we have to show this direction. So according to our steps, the procedure, first what we have to do is draw the unit cell. Second step is we have to decide the origin. Now in this case we need a positive x, negative y and z. Accordingly we have to select the origin. So this should be origin. This is the origin. Then we have to show the axis, and as I told you, if this is the origin, this side of the origin is positive. Then y-axis, this is x, this is y, and this is z. Now as I told you earlier, this side of origin is positive y, this side of origin is positive z, this side of origin is negative z, and this side of y origin of is negative y. And this is what we want. We want positive x, negative y, and z. Then let's start our journey. So let's start from the origin, and we have to move distance 2. Here is the x index is 2. Distance 2. Not only this, first we have to select the value of A. A is equals to 2. Then start the journey. Move a distance 2. That is the complete this distance is 2. So distance 2 along positive x. Then distance minus 2 along the negative y. because from here to here is 2, but we have to move only half of that, that is 1. So you reach at this point. So as you can see here, we started origin to from origin, move distance to along x, move distance to along negative y, and move distance 1 along negative z, and we got this point. Then as you know, the direction is going through origin and through the point so obtained. So this is the direction. Direction 2 bar to bar 1. Let me show some more directions. First, origin, and instead of drawing the direction, I will draw direction directly without the Miller indices, and we will identify those directions. So I am randomly drawing some directions, and let us find Miller indices of this direction. We know that, the direction starts from the origin. Directional vector starts from origin. And for all these three directions, this must be the origin. Now see this direction. We have moved some distance, say whatever is the value, that distance along the x-axis. Let me show the direction. If this is the origin, then let us mark the axis. This would be obviously x, this is y, and this is z. So we are moving some distance here along the x-axis, and from that point move some distance along the y-axis, and we got point, and the direction vector is passing through that point. So obviously the direction of this would be 1, 1, 0. Similarly, see the another one. From this point, if you move the distance a, then we get this point. This is origin. And so the direction, Miller indices of this direction is 1, 0, 1, and obviously this one will be 1, 1, 1. To get this, what I have to do, travel the distance 1 along x-axis, then 1 along y-axis, and then distance 1 along z-axis. You got this point, and so that direction is 1, 1, 1. So this is how you're going to find the direction. In the last lecture, we have studied, the family of planes. Similarly, there is a family of directions also. There is a family of directions. And this family of directions is denoted by this bracket, that is called bra and tail bracket. So family of direction 1, 0, 0, family of direction 1, 1, 0, and family of directions 1, 1, 1. How many directions would be in this family of directions? Obviously 1, 0, 0, 0, 1, 0, 0 0 1 bar 1 0 0 0 bar 1 0 and 0 0 bar 1. So there are total 6 directions in this family. Similarly, you can find for 110 there would be 12 directions. You can write that. And for this 111 there are 8 directions. You can write that directions. So in this chapter you must have noticed the importance of the bracket. As you know that if the bracket is curved bracket, then that indicates indices of Miller plane. And if there is a curly bracket, then that indicates family of planes. If there is a square bracket, then it is indices of direction. And if it is a bra and ket bracket, then it is family of direction. So every time you need not have to say that this is the Miller indices of plane or this is the Miller indices of direction. Bracket itself indicates whether it is a plane or a direction. Then in this next I am starting interplanar spacing. Interplanar spacing, which is denoted by D suffix HKL. This is a symbol for interplanar spacing, and this HKL denotes whose interplanar spacing it is. And this interplanar spacing is nothing but a normal distance between the two consecutive parallel planes. Okay, it is nothing but normal distance between two consecutive planes. Parallel planes. So that is the interplanar spacing. Now to find the interplanar spacing, again I have to draw a unit cell. I will draw it slightly different orientation. So this is the unit cell. And let's say that this is the origin over here, origin O, and if that is the origin, then you have to mark the axis. This is x-axis, y-axis, and z-axis. So these are the three axes, x, y, and z. In this, I am showing you the plane, and the plane is this is the plane. And I am going to draw normal to this plane from the origin, which is this. Let me show by different colors. This point is N. So this point is N. So this ON is normal to the plane. Let us name this plane as a ABC plane. This is A, this is B, and this is C. ABC is the plane. This ABC is Miller plane which belongs to family of planes having Miller indices HKL. So Miller indices of this plane is HKL. So if you know the Miller indices, then you can find intercepts on x, y, and z axis. So in this case, we don't know if it is a cube. So A is not equals to B is not equals to C. And so its x-intercept of this plane is x-intercept is nothing but length OC. So from this to this, that's OB, length OB, this length, and that is equals to A by H. A is not 1, so intercept is A by H. Similarly, y-intercept is length OC from this point to this point is the y-intercept, and that length OC is P by K. Z-intercept is length OA from this point to this point. O. A is the Z-intercept, and so that length is equals to P by L. So we got the intercept of this plane ABC along x, y, and z axis. Then let's say the angle, let's say alpha dash. Alpha dash is angle between normal and x-intercept. You can say x-axis also. So this angle here is alpha dash. Let's say beta dash is angle between normal, normal is OM, and y-intercept or y-axis. Similarly, gamma dash is angle between normal OM and z-intercept or z-axis. So these alpha dash, beta dash, and gamma dash are the angles between normal and x, y, z axis respectively. So this angle here is beta dash. and this angle here is gamma dash. These are not the interfacial angles, they are different. Then from the diagram you can find the value of cos alpha dash, cos alpha dash, cos beta dash, and cos gamma dash. Now from the figure here, cos alpha dash, this is the angle alpha, and cos of alpha dash is nothing but length OM, which is a normal, divided by length OB, which is intercept. Similarly, cos beta dash is length of normal OM divided by length OC, which is y-intercept. And this cos gamma dash is equals to length ON upon length OA. OA is z-intercept. Now what is this ON equals to? What is ON? ON is normal drawn from the origin to the plane, and that is equals to the interplanar spacing DHKL. It is a normal, and which is equals to D suffix HKL. So ON is nothing but normal distance between two parallel planes. We have shown here, I have shown here, ABC is one plane. If the next plane will pass through, that point O, and so ON is equal to the interplanar spacing. So normal to that plane is passing through O. So there could be many parallel planes. So ON is nothing but interplanar spacing DHKL. And so let us write the value of cos alpha dash, which is D suffix HKL, and here we know that this OP is A by H, or we can write H D suffix HKL upon A. Similarly, this is D interplanar spacing divided by B by K, and this is interplanar spacing divided by C by L, which we can write as K into interplanar spacing divided by B, and this is L into interplanar spacing divided by C. So we got the values of cos alpha dash, cos beta dash, and cos gamma dash. And you know the trigonometric equation that cos square alpha dash plus cos square beta dash plus cos square gamma dash is equal to 1. We know what is the cos alpha dash over here. So cos alpha dash is h into d suffix skl divided by a square plus k interplanar spacing divided by b square plus l interplanar spacing divided by c square, and this is equals to 1. We will take common here. Common would be d square d suffix HL square, and that is equals to, not equals to, that is into bracket. Let us write for this s square upon a square plus k square upon b square plus l square upon c square which is equals to 1 upon this quantity s square plus k square plus l square upon, let me rewrite this, divided by s square upon a square plus k square upon b square plus l square upon c square. Now this is for any crystal system. For cubic crystal system, you know that A equals to B equals to C, and therefore B square is equals to A square upon H square plus K square plus L square, or D suffix HKL is equals to A upon square root of S square plus K square plus L square. So this is the interplanar spacing, and you can find interplanar spacing for different planes. Suppose this is D suffix 111. Miller indices of the plane is 111. Then that is equals to A upon root 3. Similarly, for D110 is equals to A upon root 3 from this formula. And D of 1